Today's lecture is on the bias-variance trade-off. Without mentioning these words, I'll only mention penalization in the last sentence. I'll present this phenomenon in a very simple setting where we have a population of just two observations, where the expected value is 1.5, the observations are 1 and 2, and we will draw just one sample from this population and try to compute the average. And the conclusion will be that if we compute the average of the sample and we say that this is our prediction for the average in the population, this is not the best strategy. So this is an unbiased estimator, but this is not the best estimator. And the underlying reasons are bias and variance trade-off. But we'll see how this goes. So we have this population, and we can have two possible training sets of size 1. This is training set 1, just 1 appears in training set 2 as that observation 2 appears. When we have a data set from a population, we have just one data set. So originally we have to start with just having one data set to compute this experiment. This data set could be training set 1 or training set 2 with 50% probability. But we don't know in the beginning of the experiment which one will occur. Now, let's say we have an unbiased estimator. So our prediction, so for the average, which we say is mu hat, our prediction for the mean is what we observe. So if we see 1, we think that the average of 1 and what is on the other side of this coin is 1. And if we happen to see 2, we say that the average should be 2 of this coin and the other side, because maybe we don't have additional information. The truth is we do have additional information, but I'll speak about this in the end. So if we don't have another information, this is optimal, but we do have other information here, which will make sure that the unbiased estimator is not optimal. So let's see, if we have prediction 1 on the test set, which is the population itself, let's say it's a huge test set, which is the population. Everything could happen is that 50% of the time we can have 1 and 50% 2. For a test set in the other branch, it's exactly the same test set. And when our prediction is 1, the squared error on the test set is this, on the second is this, it's actually 0.5. Is the expected prediction squared error from training set 1, and it's again 0.5 from training set 2. We don't know if we start with training set 1 and training set 2. So at the beginning, before we get one data set, we know that the expected prediction squared error over these training sets is the average of these two, which is 0.5. Nothing strange. Now, if we start with the same experiment, we say our prediction for mu hat is alpha times whatever we observe. So it's alpha times 1, alpha times 2. This is a biased estimator when alpha is not 1. What happens? We have a test set. Now prediction is either 1 minus the prediction, 2 minus the prediction, or it will be again 1 minus the prediction, 2 minus the prediction squared. In this case, the expected prediction squared error is half of this and this for training set 1, and half of this and this for training set 2. So on average, since we don't know if we start with training set 1 or training set 2, over the training set, the expected prediction squared error is half the error in training set 1 and half of training set 2. So do we win anything with this alpha? We will win if we use extra information. I'll tell you what information extra we use, and we'll demonstrate what will be optimal alpha on the next slide. So here, the only information we use to predict mu, the mean, is the number that was observed. So we see 2, we predict 2. We see 1, we predict 1. Here we use another information. So the number that was observed, but also we assume that the unobserved member of the population, so what we don't observe, the other side of the coin, is different from the current one. So we just assume that y's are not a constant, which in statistics is always the case. So if we observe 1 and we assume that on the other side is not 1, we already have extra information, and alpha will happen not to be 1. Let's see how this goes. The optimal alpha, it was proven in another video, but the optimal alpha, the result is the following. Alpha is this term here when we draw 1. So if we draw 1 and just assume that on the other side we have a question mark, this is the optimal alpha. And if question mark is 1, we just see that alpha is equal to 1. But if it is not 1, alpha will be between 0 and 1. It will not be 1. And alpha will be called a penalization factor of an unbiased estimator. So in this case, the initial set is T1. The variance of mu hat means the variance of the unbiased estimator, which is mu hat is from the first set 1, from the second set 2, and the variance of it is 0.25. And when we know that the question mark here is 2, this alpha becomes 0.9. If we start with the other possible training set, we have 2 and question mark, alpha is equal to 2 plus the question mark, etc. This is exactly the same conclusion. Alpha will be equal to 0.9. It's not surprising. If our initial estimator is unbiased, alpha should be equal to mu squared divided by mu squared plus variance of mu hat. So this is something that is between 0 and 1. Just in the only one exception is variance of mu hat is 1. We'll discuss this shortly. But in general, alpha is between 0 and 1. For the biased estimator, this is the optimal alpha. So you can see that it will reduce to unbiased if we substitute mu for expected value of mu hat over t. So we can penalize also a biased estimator in an optimal way, not only unbiased. The conclusion is that optimal alpha is between 0 and 1. Actually, it will be 0 when mu is 0. So if mu is 0, we want our prediction to be 0. So alpha should be 0. When it will be 1. When it will be 1 when variance of mu hat is 1. This occurs only in two situations: when y's are constant. So if we observe, or if the population is 1 and 1, we will compute our mu hat as being 1, 1. So the variance of 1, 1 will be 0. But this is not interesting because in statistics, y's always have some variance. The other possibility, the variance of mu hat to be 0, is if all the training sets are the population, so that we compute mu hat in exactly the same way from any training set. But the training set is never the population. If we have the population, we don't have to compute, we can compute the mean, not estimate it. So both of these cases are irrelevant. Thanks for listening.